So in the last video, I talked a bit about this new continuously variable LCR meter. And the neat thing with that is that you can sample the inductor at any frequency you want between 100 hertz and 100 kilohertz. And what this allows you to do is determine the frequency where the given inductor has the highest Q factor. So I can't remember now what I actually showed and what I was saying. Oh, I should talk about that. But you know, one area where that's useful is like, for instance, if you're spinning a rotor, you know, like Bedini SSG or Adams pulse motor style, you can figure out exactly how long you want the pulse to be in order to get the most back EMF back. And one thing that I didn't show, I'm fairly certain, but that if I get nothing else out of this project, this Q project, this is probably something very useful right there, is I used a random coil that I'd been spinning rotors with before, and it had a Q as an air core of a bit over 60, and if you put in welding rods, of course the induction goes up, but the Q goes down to about 15. Now, what I didn't show, here's a secret. If you use ferrite instead of, and this actually is really useful for people doing like the Adams motor stuff. If you use ferrite, you get that nice increase in induction, and you don't lose much Q at all. The same coil. Now, granted, you want to wind the coil differently as we understand more, but the same coil had a Q factor of about 60. So before we get to the other stuff, just to wrap this up, if you have a Q factor of about 15, what does that mean for you? That means, I always get confused. Okay, I got it right now. That means if your cap's starting at 10 volts, it'll go down to 0. Q factor of 15, it would bottom out at about -9 with a Q factor of 15. So that's really cool, because if you were spinning it, if you cut it off at 0 and shunted it out and you were running at 10 volts, then that would be, you would get 9 minus the 0.6 voltage drop across the diode, so it would be about 84% back. Now, the other thing you could do is just have it shunt right back into the cap, be back at 9, except for it's negative, but now you have a magnet of opposite polarity come past. If you are at a Q factor of 60, like you see with an air core or with ferrite, easy, easy peasy, just not even trying to do anything, just using ferrite or an air core. Now, the air core is a really small pulse, so you want to run it at high voltage. The ferrite does slow it down, but you still have the high Q factor. And now you get back approximately 97.5%. So it go from 10 to 9.75. Q factor at 30 would be about 9.5. This is approximate, but that's about the trend. So Q factor 120 would be like 98.5 or whatever. A little more than that. So with the ferrite, you could get back 97.5. With the iron core, about 90. And you'd say, well, it's 10%, versus 2.7. You've only improved 7.5%. The other way to look at it is you've improved fourfold, and that's probably the better way to look at it. Let's stop on the, I guess it didn't get a lot of views, but I thought it was interesting stuff. Let's get to something that I want to talk about for a while now, which is what are the things that you can do to improve Q factor, and we need to gain an understanding of skin effect and proximity effect, and both of those come into play extensively with Q factor. So I don't know if there's anything else I should be saying to set it up, but let's just go into it, and I think we can just go into it now. Okay, thanks. So let's first talk about what is the skin effect. And this is from All About Circuits. Sounds good to me. It's important to remember as we go through this that the same phenomena causing skin effect, causing proximity effect, is what causes your displacement current. You know, if you're calling it a switch mode transformer, your radiant effect, if it's, you know, you're calling it a Bedini schoolgirl circuit, it's the same phenomena. So we'll get to that in a little bit, but first let's just talk about skin effect from this write-up. And it's where alternating currents tend to avoid travel through the center of a solid conductor as you increase frequency. So here they're showing, here's the cross-sectional area of a conductor when it's just, you know, DC resistance. You've left the inductor just going for 10 seconds. Here's where it's a slow frequency AC resistance, and here is the cross-sectional area of the conductor with a high frequency AC resistance, and you see that it's much, much smaller. So of course the wire diameter hasn't changed. It is just that the functional amount of copper that you're pushing current through decreases as you increase the resistance. And we can go to an American wired gauge chart. And I like this one. It's missing one thing, but aside from that, I like it. It doesn't give you the weight of the wire. So if you go down here, let's take like 20 gauge. It's hard to see. No, we can see it. There's the conductor diameter, there's the ohms per 1,000 feet. This is what we're interested in regards to our current topic. Maximum frequency for 100% skin depth for solid conductor copper for 20 gauge is 27 hertz. So what that means in practice, and we could go through all the equations, but there's no need to, is that I said 27 hertz, I meant 27 kilohertz. At 27 kilohertz is where the resistance begins to increase for 20 gauge wire. And up to there, you're still at here or at here. So you can kind of get an idea for whatever gauge wire how fast you can go before skin effect begins to predominate. And you can see if you start to go with thick wire, I mean, here you're at 5 kilohertz at 13 gauge, or 7 kilohertz at 14 gauge. If you go down to like 8 gauge, you're at 1.65 kilohertz. So it starts to slow down a lot before, you know, when you see skin effect begin to become an issue. So we can go to Wikipedia. I don't like them for some things, but I really like them for other things. And it's not bad here. Skin effect is the tendency of an alternating current to become distributed within a conductor such that the current density is largest near the surface and decreases exponentially with greater depths. Here they are showing by diagram that one skin effect is where the current decreases by 37% of the value at the surface. So if we go back to this chart, you know, at say 20 gauge, at 27 kilohertz, is where at the center, right at the center there, is where it would be decreased 37%. So that's why up until you get to that frequency, you don't see a big change, dramatic change, because only at the center there it would be decreased by about a third. But, you know, with this one, for this particular frequency and this particular diameter of wire, you can see all of the current is just flowing on the outside here. And they note then, of course, that skin depth depends on the frequency of the current. And as frequency increases, current flow becomes more concentrated near the surface. And they also say that at 60 hertz in copper, skin depth is about 8.5 millimeters. So in other words, unless you have a wire that, well, if we use diameter, it would be like a wire about more than 1.7 centimeters in diameter, you're not going to run into significant skin effect at 60 hertz. 600, 6,000, 60,000, you're going to run into a heck of a lot. Now, of course, why we care about this in terms of Project Q is that as you increase resistance, because you are decreasing the functional resistance of your wire because of the skin effect, increasing resistance, just like placing a damp cloth on a bell, decreases Q factor. So you want to stay away. You want to stay away from increased resistance from skin effect. Now they mention one way here that you can get away from this skin effect by using Litz wire, which is stranded wire that's twisted around. And we'll just leave it at that right there. But if instead of having one big wire, you have 10 wires and you twist them, then you get rid of most of the skin effect. And just to cover one more thing here, that it's caused by the same thing that's causing your back EMF spike. That a current in a conductor produces a magnetic field. This time it's in and around the conductor itself, where when the intensity of the current in the conductor changes, the magnetic field changes, and this creates an electric field that opposes the change in current intensity. So it's the same phenomena that creates your back EMF spike, except for this time it's having an effect on the very wire itself. And the intensity of current in a conductor changes, the magnetic field changes. This creates an electric field on that very wire that opposes the change in current intensity, and that leads to the current being driven to the outside of the wire. I'm like moving my hands apart, I don't know why. And you know, we can calculate it here. They give us the formula. We don't need to, because we've got a continuously variable LCR meter where we can sample it at whatever frequency we want and read what the resistance is. And that'll give us both the decrease in resistance from the skin effect as well as the proximity effect. And the last thing I will say before we go to proximity effect is that skin effect is like the last one you come across. Proximity effect you come across much sooner, and it's a much stronger and dramatic effect. And proximity effect is the same thing, except for you got this wire right next to another wire, and it's inducing a current in the other wire or the other 15 wires right around it that oppose oppose the flow of current in this wire. And so the proximity effect is generally more significant and dramatic than the skin effect. So first you want to deal with proximity effect, and then you want to think about dealing with proximity effect. But first deal with, what did I just say? First you want to deal with proximity effect, then you want to deal perhaps with Litz wire, with skin effect. So now let's take a look at proximity effect and how you can engineer for that to improve Q factor. So proximity effect. Now, if you have, say, two wires where they're both going in the same direction, not only do you have skin effect, but you also have this proximity effect where, so here's two positives and they're pushing the current out towards the sides there. Here's a positive and negative. They're pulling them in there. So again, you have less than the conductor diameter that's conducting electricity. So let's just see what they say. An electromagnetic phenomena causing non-uniform distribution of AC current in multi-turn windings, which can lead to a significant increase of power loss. You could also say a significant increase of resistance, reactive resistance, as compared to DC current. This is caused, this is additional power loss is called proximity loss. And this one's important. Proximity effect can be several orders of magnitude, not, several fold, several orders of magnitude greater than skin effect. And this is one where I had to look up, and I finally found one of the references that wasn't paywall. It grows exponentially with the number of layers of wire in the winding. So let's just read that one more time. It can be, proximity effect can be several orders of magnitude greater than skin effect, and it grows exponentially with the number of layers of wire in the winding. And while we won't go through the whole thing, I did look up all these. Most of them were behind paywalls, but this one, number 4, Lloyd H. Dixon, this one this was out of Texas Instruments from some years ago, goes through all that. And he mentions another thing, this gentleman, that is not in this write-up, which I found interesting, was that in terms of proximity effect, if you use Litz wire, which would reduce the skin effect, the Litz wire is actually viewed as like multiple potential places to interact, and it actually aggravates proximity effect. So Litz wire, if you're not getting rid of skin effect, actually makes things worse, and proximity effect can be several orders of magnitude greater than skin effect. So if you don't think about it and know what you're doing with Litz wire, it doesn't make things better. It can actually make things worse, as this gentleman, we won't go through the whole write-up, but this gentleman notes there in his research. So this right here pretty much describes for you what's going on with proximity effect. And you can imagine, I don't know if we can find one. Uh, what they show is that as you add more layers, the proximity effect becomes more of a problem. I don't know. But if you have 3 layers, the proximity effect is worse because it hits here and then it hits the next layer, and then this one's also hitting there and hitting the next layer. So adding layers makes things real. That's why it becomes orders of magnitude greater than skin effect. Now I'll just mention this. It's not mentioned in the write-up. It's not something I've done anything experimentally with. I'm just looking at it. Yeah, and I'm saying, there you go thinking again. But let's look at this one. Positive, negative. This is pulled into here. This is pulled into here. What if you had a third one, positive, right here? What would that do to this negative? Well, this is being pulled there, and then you have another positive. It's pulling it there. Wouldn't this put it right back in the center? I'm just asking, babe. Sorry. I'm just asking. I haven't done the experimentation on this, but if you did that, say in some sort of like counterwound arrangement, wouldn't that just get rid of all of your proximity effect? And you could even set it up sort of like a salt crystal, boom, 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 boom. You know what I'm talking about. And you could have multi-layer coils as well. But that's something to determine and to see whether that does that, and hence greatly improves the Q factor. Q. So it would pull it, if you had another one here, for this one there, it would end up looking like that. Then if you had that set up, that's when you would use your Litz wire to also mitigate skin effect.